In our previous lecture, we talked about, for a given two-port circuit, the resistance matrix representation and also the conductance matrix representation. And those are not the only two types of representations. We have also some other ways to describe, and certain representation may be better than certain other representation depending on the situation. So it's good to know as many representations as possible. And today we will see some three further representations for a given two-port. Okay. The first class is called hybrid representation, where we obtain the hybrid matrices for a given two-port circuit. And what hybrid matrices are, we'll see in a minute. Suppose that this is our LTI resistive two-port. Okay. Plus minus V1, plus minus V2, I1, I2, and we assume always that the port condition is satisfied with this. If this is I2, then this current in that direction must be I2, and same for the first port. Okay. So this is LTI resistive circuit, and it contains no independent sources. So those were all the assumptions that we make in order to be able to talk about new representations. Okay. The resistance parameters representations was you express voltages in terms of currents, that is voltage vector V equals some matrix times the current vector, and that's the matrix we call the resistance matrix. The conductance parameters representation were such that we express current in terms of the voltages, that is the current vector I1, I2 equals some matrix 2 by 2 matrix times the voltage vector V1, V2, and that matrix we call the conductance matrix. Okay, now today we're going to introduce three more matrices. Okay, we begin by hybrid matrices. There are two types of hybrid matrices. One is called type 1, the other is type 2. Type 1 is such that you consider the voltage of the first port and the current of the second port as your output, and current of the first port and voltage of the second port your input. Okay, and then they satisfy a linear relation. In that relation a matrix appears, and that matrix is called the hybrid matrix, okay, or type 1 hybrid matrix. So this is H11, H12, H21, and H22. This matrix is denoted by, in general, capital H. Now, if you consider this as the output and this as the input, in that case, we have I1 V2 equals some matrix times V1 I2 vector. And that matrix is denoted by H prime. Okay, and the entries are H11 prime, H12 prime, H21 prime, and so on. Okay, and H prime equals H inverse, provided that this inverse exists. Okay, if inverse exists. Okay, if, for instance, H you figured out an H, but it's not invertible, so that means there is no type 2 hybrid representation for the particular two-port. Okay, but if inverse exists, then there is, and H prime equals H inverse and so on. So these are the two other representations, and we have one final representation that we want to talk about, and that's called the chain parameters representation, or transmission matrix representation, chain parameters. Okay. And in that case, the input and output are as follows. The inputs are given at V2 and minus I2, okay? And together they make our input matrix times the representation matrix gives us the transmission, gives us the output, okay? And the output is V1 and I1, okay? Now, transmission matrix, this is represented by T, and unlike the previous cases, entries are not T11, T12, T21, T22. Instead, they are A, B, C, D. Okay, it's just convention, and so we're going to stick to the convention. Okay, A, B, C, D are what we use to denote those entries. Okay, now let's see a couple of examples where we use these new representations so that we understand them a little bit better. First example is about chain parameters. Consider ideal transformer, and for the ideal transformer, let's try to obtain the T matrix representation. Okay, find the matrix T, or the chain parameters for the ideal transformer. So what was an ideal transformer? This is our two-port component. Okay, this is the first coil, V1 and I1. This is the second coil, V2 and I2. Okay. And here somewhere we must be given the turns ratio, N1 to N2. Okay, now from this we will obtain the entries A, B, C, D, and for that what we will use is the only thing that we can use, namely terminal equations for the ideal transformer. Okay, and let's write down terminal equations. We have the voltage equation where the ratio of the voltages equals the ratio of the turns ratio, and we have the current equation where the ratio of the currents is minus the inverse of the turns ratio. And it works N1 I1 plus N2 I2 equals 0. Okay. So this and that, let's rewrite those two equations where we express V1 in terms of V2 and minus I2. Likewise, let's express I1 in terms of V2 and minus I2. And if you can obtain such equations, then from those equations we can easily gather the entries of the transmission matrix. Okay. Now, this voltage equation gives us following: V1 equals N1 over N2 times V2. Okay. So therefore, we were able to express V1 in terms of V2 and I2. In fact, V1 doesn't depend on I2. So what we have is V1 equals this thing times V2 plus 0 times minus I2. Therefore, the first row of transmission matrix must be N1 over N2 for A and 0 for B. And the current equation will give us the second row. Let's express I1 in terms of I2 and V2. So we have I1 equals minus N2 over N1 I2. And then putting these two equations into the matrix form will directly give us the transmission matrix. So let's combine these two equations somewhere here. So we have V1 I1 equals V2 minus I2. Okay. For the first row, we look at the voltage equation. What we have is V1 equals N1 over N2V2 plus 0 times minus I2. And for the second row, we look at the second equation. I1 equals 0 times V2 because it doesn't depend on V2 plus N2 over N1 times minus I2. Okay, so this is therefore N2 over N1. Therefore, this matrix T is the transmission matrix representation for the ideal transform. It's diagonal. Now let's have an example with hybrid representation. Find, excuse me, still we have another example with transmission matrix. Example, find the input resistance. For the following one port. Now this one port is such that it's obtained from a two port by terminating the second port by an LTI resistor. Okay. Now here we have a two port circuit. Okay, and this two port circuit V1, V2, I1, I2. And this two-port circuit is such that we know, or we computed beforehand, its transmission matrix parameters. Okay, therefore we know what A, B, C, and D are in this relation. Okay. Now this two-port is taken, and the second port is terminated by an LTI resistor. By being terminated, we mean you simply connect an LTI resistor to the second port. Okay, and the resistance is R. Now, after this operation, note that this whole thing can be considered now as a one port. Okay, and the port terminals are here, V1, I1. Since it's one port, and since it doesn't contain any independent sources, therefore it can be represented by an input resistance. And the question is, what is that input resistance? We have to figure that out. Okay. R in. Okay. Where V1 I1 equals V2 minus I2, A, B, C, D. Okay, so we have the transmission matrix parameters, A, B, C, D. Okay, so what's R in? R in is the ratio of V1 over I1, so by definition. And now, therefore, what we will do is, we will try to obtain this ratio, okay? But we have other unknowns, okay, in the circuit, like V2 and I2. By using this equation and also the terminal equation for the resistor, we will try to get rid of those dependencies and hopefully obtain this ratio, V1 over I1. In terms of what? In terms of 5 parameters, A, B, C, D, and the resistance of that resistor. Okay, so what we do is, let's write everything down. Let's write everything that we can. Okay, so what we have is V1. Let's write V1 in terms of other things. And for that, what we do, we look at the transmission matrix equation. Okay, so what's V1? V1 is A V2 minus BI2. A V2 minus BI2. Let's do the same thing for I1. Okay, I1 equals CV2 minus DI2. Okay, and then if you take the ratio now, V1 over I1, not that you cannot get rid of this V2's I2's by cancellation, because we have two different variables, V2 and I2. Okay, so what we have to do is we have to do something else, and that something else comes from the Ohm's law for that resistor. Now, this voltage is labeled as V2, and clearly it's the voltage, plus minus voltage of this resistor, okay? Now, this is VR, let's say, and VR is V2. And how about IR? Okay. So that VR equals R times IR. How about IR? This is I2, this is IR, therefore IR is minus I2. Okay, therefore we can write V2 in terms of I2, and it's the following: V2 equals minus R I2. Okay. And now, by replacing V2 by minus R I2, everything here and here becomes in terms of I2, and then when you take the ratio, I2s will cancel out and you obtain the input resistance in terms of the parameters. So let's do that. At second stage, we rewrite these equations by replacing V2 by minus RI2. V1 equals minus ARI2 minus BI2, and V2 equals minus CRI2 minus DI2. Okay, so that equals minus AR plus BI2, and this equals minus CR plus BI2. Okay. Excuse me, this is I1. Okay. And now we can take the ratio of V1 to I1. V1 over I1, which is by definition the input resistance, equals this over that. I2s will cancel, these minuses will cancel. So what we have here is AR plus B and CR plus D. Okay, so that's the input resistance for this one. Okay. Now, what we're going to do now is we're going to combine the previous two examples and obtain input resistance for the following one port. Okay. Now, for this case, we have input resistance in terms of A, B, C, D, and R here, and for the ideal transformer, we have the transmission matrix parameters A, B, C, D here. Okay. So, in our third example, we're going to now combine the previous two examples. Okay. That is, we have an ideal transformer. We take an ideal transformer. Okay. N1 and 2. Okay. And then what we do is, suppose that this is port 1 and this is second port. What we do is we terminate the second port or second pair of terminals with a resistor whose resistance is R. And now, after that termination process, this device becomes a one-port circuit. Therefore, it has an resistance. And now we ask for that. What's the input resistance for that configuration? Okay, so combining the previous two examples, okay, where the results are still on board. Here we have transmission matrix parameters for the ideal transformer, and here we have the input resistance for such termination. We can write the following: R in equals AR plus B over CR plus D. Okay. So that's the general formula that we obtain, and for the ideal transformer, we know what A, B, C, D are in terms of the turns ratio, N1 and N2. And they are what? A is N1 over N2, N1 over N2 times R. B is 0 plus 0. Then C is 0. Okay, and D is N2 over N1. Okay, and now simplifying that term immediately gives us N1 over N2. Another N1 over N2 when we carry this upstairs, so that makes N1 over N2 squared. Then times R is the answer. Okay. Let's see another example. This time in terms of hybrid parameters. Okay. Now we have the following. One port which is obtained from the two-port for which we're given, or we have, let's say, previously computed, the hybrid parameters, hybrid representation. Okay. Plus minus V2 plus minus V1, I1, I2. Here we have 1 ohm. That's how the second port is terminated. And to the first port we connect something else. This is 10 ohm minus plus 16 Ix. And the control variable is here, Ix. Okay. Now for this two port, we know we're given the hybrid representation where V1 I2 equals hybrid matrix times I1 V2. Okay. And the hybrid parameters are going to be 4, -2, 2, 3. Okay. Now this thing, since it has a hybrid representation, doesn't have independent source inside. Therefore, this whole thing considered as a one port doesn't have independent source inside. And it's also LTI resistive. Therefore, it must have an input resistance. Okay, and the question is, what's that input resistance? Okay. Now, there could be many ways to find the answer, but let's do it in such a way that we decompose the problem into simpler sub-problems, and then finally we combine all the results that we obtain. Okay. So, therefore, the first step could be the following. Okay. The first step is such that let's forget about this dependent source and this 10 ohm resistor and just consider this as a one port where a two port is terminated by the following resistors. Therefore, this thing seen from the first port terminals must have an input resistance itself. Okay, so as a first step we can compute that input resistance and then take this out and replace that thing by that input resistance. And for that much simpler one port, we can go ahead and figure out the original input resistance that we are asked. Okay, so therefore we're decomposing this problem into two simpler sub-problems. Okay. So step 1, therefore, is the following. What's the input resistance for the following configuration? Okay, plus minus V1 plus minus V2. This is I1, this is I2. This here is 1 ohm. Okay, so to see how these are carries along, let's call it an R, okay? Instead of 1 ohm. At the very last step, we can replace R with 1. And then, now what we try and figure out is this input resistance, let's call it R1, okay? And R1 is V1 over I1. Okay. So, what we have here is, this is V2, this is I2, this is minus I2, and this voltage is V2. Therefore, because of that resistor, this voltage and this current are related to one another, namely V2 equals minus R I2. Okay. What else? We have equation 1, therefore, and if this is equation 2, by 1 and 2, we can write V1 I2 equals the hybrid parameters 4, minus 2, 2, 3. And then here, instead of V2, we can write minus R I2. Okay. So that's I1 and minus R I2. So that we get rid of this V2. Okay. So we have fewer number of unknowns thanks to the Ohm's law that we used. Okay. Now what we will do is, from this equation, we will try to obtain this ratio, V1 over I1, and that will give us input resistance. So let's go ahead and do that. So let's write those equations individually. V1 equals 4I1 plus 2R I2. Okay. And I2 equals 2I1 minus 3R I2. Using the second equation, we can express I2 in terms of I1, and then we can replace that expression in the first equation, and then that first equation becomes only in terms of V1 and I1. And since from that equation we can easily obtain the ratio of V1 over I1, we will have been done. Okay, so let's do that. So the second equation implies that I2 equals 2 over 3R plus 1 times I1. Okay. So that's I2 in terms of I1. And then, okay, so let me squeeze it here. Okay. Then what? Then V1 equals 4I1 plus 2R times, now instead of I2 we write that 2R times 2 over 3R plus 1 times I1. Okay. And that's 4 plus 4R over 3R plus 1 times I1. Therefore, the ratio V1 over I1 must equal this. And then finally, you plug in I equals 1. And that gives you the numerical value for the input resistance, okay, R1 that we're trying to compute. Then R1 equals V1 over I1, and you set R equals 1 ohm, okay, which is 4 plus 4 over 4. So 4 plus 1 gives you 5. Okay. Hence, the first part of the problem is complete. Now we can move on to the second part. Step 2. Step 2, compute the original input resistance that we were asked using the following simpler one port. Okay. Okay. To this pair of terminals, we previously had this piece. Now we're expressing this piece in terms of its input resistance, because we can. Okay, so what we have here is R1, which we compute to be 5 ohm. Okay, R1 equals 5 ohm here, and here we have 10 ohm. This is Ix. This is, let's call it I1, and here we have V, and this is I. Okay, and what we're trying to figure out is we're trying to figure out R in minus plus 16 Ix. Okay, now figure out R in equals the ratio of V to I, and using this simple one word, we will now figure out that. Okay. So 10 Ix equals 5I1. Why is that? Here we have voltage, here we have another voltage, and those two resistors are parallel, therefore this voltage must equal that voltage. So this voltage is 10 times Ix, this voltage is 5 times I1, and they are equal to one another, and that gives us the ratio of the currents. Okay, 10 Ix equals 5I1, meaning that I1 equals 2Ix. And then what's I? I equals Ix plus I1. So that gives us Ix plus 2Ix, 3Ix. If we can also express voltage in terms of Ix, and when we take the ratio, the Ix will cancel, and then we obtain the input resistance. And it turns out that it's quite easy to write V in terms of Ix. This voltage equals this voltage plus minus plus this voltage plus minus. Now this voltage plus minus is minus 16Ix, and this voltage is 10Ix. Okay, the sum therefore is minus 6Ix. Okay, so we have the current in terms of Ix, we have the voltage in terms of Ix, therefore the ratio will give us the input resistance. So Rin equals V over I, and V is minus 6Ix, I is 3Ix, and the ratio is minus 2 ohms. Okay. Now that we obtain a negative resistance, which is possible when we have a dependent source. Okay. Which we have. Okay. Now let's talk about the power of the two-port. Quickly, power of two-port. Okay. Note that previously we defined the power of a two-terminal component by simply the product of the voltage and current. Now, when we when we want to talk about the power of two-port, what we would mean is we mean the sum of all the powers of individual components inside the circuit, the two-port. Okay, so suppose that this is our circuit, two-port, that doesn't contain any, well, independent sources. In fact, this thing is also true for the case where we have independent sources inside. Anyway, so this is V1, this is I1, so here we have V2, and this is how we label the current. The voltage and current at the port terminals. Now, for this circuit, we define a quantity that we label P sub n, and indicates the circuit. B, the sum of powers of all individual components inside that quantity we define as, or we using to define what we call the power of two-port. Now this definition of power of two-port indicates that to figure out this power, all you have to do is you go component by component inside and compute each power and sum all those numbers, and the result must give you the power of two-port. Okay? So if this has many components inside, so that means you have to do a lot of computation. Okay? But it turns out that due to, or thanks to Telegrams theorem, to compute this quantity, which by definition is the sum of many sub-quantities, you don't have to look inside the one port. Okay? All you have to do is, all you have to know is just the current and voltage at the port terminals. So here we have a very elegant theorem. Which has a very elegant proof, and the proof will be left as an exercise. Okay? Theorem. The power of two-port, that quantity Pn, simply equals I1 V1 plus I2 V2. That is, you don't have to look inside N, which could be very complicated. All you have to know is just the voltage and current at the port. And I strongly suggest or recommend that you work on the proof. In fact, it's just 1 or 2 lines of proof. Okay, so I leave it as an exercise. You may assume N contains only 2 terminal components for the proof. Okay. And how you prove it is, you prove it by Telegrams theorem. Use Telegrams theorem. It could be a very nice occasion to remember what Telegrams theorem was. Okay. And now, having defined the power of the two-port, now we can define whether the two-port is passive or when the two-port is passive or active. Okay. Here's the definition. The two-port is said to be passive if Pn or this sum I1 V1 plus I2 V2 is never negative. Okay, for all possible sets of port variables. Okay, I1, V1, I2, V2. And if it's not passive, we call it active. Okay. Active if not passive, by which we mean if you can find just a single set of these 4 numbers, I1, V1, I2, V2, so that the port equations are satisfied, whatever, and the port equations depend on the internal circuit, such that this number is positive, then automatically your two-port is said to be an active two-port. Okay. Now, in the last part of the lecture, we will quickly talk about how different representations could be useful when we obtain new two-ports from a bunch of two-ports, and how to express the new port characteristics for those new constructions. Okay, so let's study therefore interconnection of two-ports. connections of 2 ports. Okay. So we'll see 3 connections: parallel, series, and cascade. And all those connections, or for each of those connections, a particular type of representation is easier to work with than the remaining ones. Okay. So by parallel connection, we mean the following: you have the 2 port here. Okay. And the port variables are labeled as V1A, I1A, V2A, and I2A. Okay, so let this be 2 port A. And suppose that for this you're given, or you computed beforehand, the conductance parameters, okay, or you have the conductance matrix. Okay, that is the current vector equals this times the voltage vector. Then we have another 2 port for which you also have the conductance parameters. Let's call it 2 port B, and voltage and current are labeled as V1B, I1B, I2B, V2B. Okay. And then you go ahead and obtain from these two ports, you obtain a single 2 port by the following connection. Okay. Okay. So this is plus minus V1, I1, plus minus V2, I2, and the connection is as follows. Now this is this terminal you connect to this terminal and also this terminal. Okay. Therefore, this, that, and those terminals all make up a single node in our connection. And then the other terminal you connect to the remaining first terminals. Okay. And that's how you construct the first port, okay, of your new 2 port. And then you do the same thing here. This is connected here and here. Okay. And then this is connected here and here. And after that connection, from those two ports, you obtain a single 2 port. And now you want to be able to express the port characteristics for this new 2 port. Okay. So let's do that. What we know is the following. First of all, first of all, what's V1? V1 is the potential difference between those 2 nodes. Okay. Now these 2 nodes and these 2 nodes, they're the same. Therefore, V1 and V1A, they are the same. Likewise, this potential difference is same as this potential difference. Therefore, that also equals V1B. Okay. So all those voltages, there's a single voltage, in fact, for the first port, and that's V1. V1, V1A, and V1B, they're all the same thing. And likewise, for the second port, V2 equals V2A, and that's V2B. Okay. This voltage equals this voltage, and also equals that voltage. How about currents? Okay. What we have is, now this current I1 equals this current plus that current by KCR. Now this current is I1A and this current is I1B. Therefore I1 equals I1A plus I1B. Likewise, I2 equals I2A plus I2B. Therefore, the current vector here equals the current vector for the A2 port plus the current vector for the B2 port. So I1A, I1B, I2A, I2B. Okay. And now we know that I1A, I2A we can express in terms of the voltages. Okay. That's GA times V2A, V1A, V2A. V2A. Likewise for this guy, GB times V1B, V2B. Okay. And then, since all these voltages are the same and that voltage, those voltages are the same, so this is V1, V2, this is also V1, V2. Since it's the same vector that these matrices are multiplying, you can combine this into the following equation: GA plus GB times V1, V2. Okay. Therefore, for the parallel connection, the conductance matrix of the overall two-port equals the sum of individual conductance matrices. Okay. Let's see also the series and cascade connections. This is called the series connection. Okay, you have this, and here you have that. You have one port, you have another one port, and then from those two separate one ports you obtain, a two port, another two port, and from those two separate two ports, by the series connection, you obtain a third two port. Okay. So here, this voltage is V1, this current is I1, by port condition, this current is I1, and then this current is I1, and finally this current is I1. So, okay, this current just follows that path. Likewise, we're calling this voltage V2, and then this current is I2 by port condition. It's I2 here, it's I2 here, and also it's I2 there. Okay. Now, if you work with the conductance parameters as before, you would run into trouble. Not trouble, but it would take very long to express it. But if you have resistance parameters, let's say RA and RB, for this connection, the overall resistance parameters is simply the sum of individual resistance parameters. And it's not difficult to show that, and it's left as an exercise. RA plus RB times I1, I2. And that's called series connection. And finally, the cascade connection is as follows. And if you have cascade connection, the easiest representation to work with is the chain parameters. Okay, and this is called cascade connection. So here you have one port. Here we have, two port. Here we have another two port. Okay. And what you do is, from those two ports, you obtain a single two port by simply connecting the second port of the first two port to the first port of the second two port. Okay. So here we have I1, this voltage is V1, and here we have V2, I2. Now if you know the chain parameters or transmission matrix for those individual two ports, then the transmission matrix of the overall two port simply is the product of those two separate matrices. So V1, I1 equals TA times TB V1 V2 minus I2. Okay, so this is the overall transmission matrix representation for the new two-pole. And it's also not difficult to show, and it will be a nice exercise to work it out. Okay. And let's end this lecture by an algebraic equation, by which I mean the following. Okay, suppose you're in the lab and you have, or you're given a two-pole. Plus minus V1, I1, I2 plus minus V2. That's good. And for this two-pole, you're allowed to make two sets of measurements. Okay, and you perform the measurement, let's say, given the following measurements on N, find the resistance matrix. Okay, the measurements that you make or that you're given are as follows: experiment 1, and then experiment 2. Okay. So V1, V2, I1, I2. For the first experiment, you obtain some set of numbers, voltages for these two entries and currents for the remaining two entries. And for the second experiment, you obtain another set of 4 numbers. Okay, it doesn't really matter what the numbers are, so let them be just arbitrary entries: 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have those two sets of experimental results, and from those measurements, you're asked to find the resistance matrix. Okay, so let's do that, and all we have to remember is the definition of resistance matrix, and then by using those 8 numbers, we can easily compute that matrix. Okay. Here is the solution. Experiment 1 implies that. Okay. Now, where does the resistance matrix appear? It appears in the equation where voltages are expressed in terms of currents. Okay, V1, V2 equals R times I1, I2. So for the first experiment, V1, V2 is what? 1, 2, and the currents are 3, 4. Okay, so whatever the resistance matrix is, we don't know it yet, it must transform this number 3, 4, the currents, to the set of voltages. Okay, how about experiment 2? For experiment 2, we have another set of data. The voltage vector equals R times, and this R and that R, they're the same because it's independent of the experiment. It's fixed parameter. The voltage equals R times the current. What's the voltage? It's 5, 6, V1, V2 equals R times the current, 7, 8. Okay. And then, once you combine those two equations, which we can because it's the same R matrix here, into a single equation, the R matrix almost automatically follows. Okay, so let's rewrite those two equations in a single equation, by which I mean the following. Okay, 1, 2, and 3, 4, 5, 6 here, and 7, 8 here. Okay, now we have a 2 by 2 matrix equals a 2 by 2 matrix times another 2 by 2 matrix, and to compute R, all you have to do is multiply both sides from right by the inverse of this matrix. Okay. Therefore, R equals 1, 2, 5 times inverse of this matrix. 3, 4, 7, 8 inverse. Okay, it's quite easy to figure out any representation, in fact, using the very definition of representation, if you're given two sets of linearly independent data.